Welcome friends. I am Professor Nupur Sinha, Associate Professor of Electrical Engineering at Government Engineering College, Modasa. In today's session, we will discuss about electrostatics. By now, I assume you are already conversant with some of the topics that we have discussed earlier. The concepts that you have studied so far will include fundamental laws of electrostatics, or as they are more popularly known, the Coulomb's laws of electrostatics. The first law states, like charges repel each other, whereas unlike charges attract each other, which means that if two positive charges are brought in each other's vicinity, they will repel each other. On the other hand, if a positive and a negative charge are brought in the vicinity, they will attract each other. The second law of Coulomb gives us the magnitude of the force of attraction or repulsion, as the case may be. It states that the force between 2 point charges is directly proportional to the product of the magnitude of the charges and inversely proportional to the distance between them. That means more the distance, less will be the force, and vice versa. We have also discussed the concepts of absolute permittivity, relative permittivity. Basically, permittivity is the ease with which electric flux can flow in a medium. The value for absolute permittivity is 8.854 into 10 raised to minus 12 farads per meter. It is a constant which you must bear in mind at all times. The relative permittivity is a dimensionless quantity, as it is a ratio of two similar quantities. Relative permittivity is the ratio of permittivity upon absolute permittivity. For air or vacuum, the value of relative permittivity will be equal to 1. The electric flux is denoted by the Greek symbol psi, and it is given as the ratio of charge divided by permittivity of the medium. The electric field intensity or the electric field strength is defined in many ways. The first definition says the force per unit charge is known as the electric field intensity. The second definition has to do with the potential gradient. It says the potential difference between the 2 points divided by the distance between the 2 points, that is V upon D, expressed as volts per meter. The third definition states E, or the electric field strength, is directly proportional to the charge and inversely proportional to the area. It is given by the equation E is equal to Q by epsilon into A. We have also come across the definitions of electric flux density, the flux denoted by psi, the density denoted by the flux per unit area expressed as coulombs per meter. The flux density is also expressed in terms of the electric field strength, as we found earlier. In the earlier slide, we mentioned the equation E is equal to Q upon epsilon A. Now, according to this definition, E is equal to the flux density divided by the permittivity of the medium. The next definition is the electric potential. Electric potential is defined as the work done in moving a unit positive charge from infinity to some point in the electric field. Hence, in the formula, the electric potential is defined as work done expressed in joules divided by the charge expressed in coulombs. So, the unit of electric potential may also be expressed in terms of joules per coulomb. And we have also discussed potential difference. Potential difference is the work done in taking a unit positive charge from one point to another point within the electric field. It constitutes the potential difference. And finally, the potential gradient. Gradient, as we all understand, is measured in terms of the slope or the fall in the potential within the electric field. Let us now go further. We start with discussion about electrostatic induction. In very simple terms, electrostatic induction means creating or generating static electricity in a material by bringing an electrically charged object near it. As you can see in the figure on the slide, say we have a conducting material as shown by the white slab on the figure, and we have an electrically charged rod shown by the red figure on the symbol. Normally, in any material or in any object, the presence of positive and negative charges are always balanced. That means the electrical property of the object is under normal circumstances in a neutral condition. That is, the positive ions are balanced by the negative ions or the electrons. Now consider a situation when an electrically charged object, as shown by the red figure in the symbol, say it is charged with negative ions and it is brought towards a conducting material slab. Now, as per Coulomb's law, like charges attract each other and unlike charges repel each other. As we have a slab of conducting material, so there are many free ions flowing in the object. Upon the approach of a negatively charged object, in the conducting slab, the ions will realign themselves so that the positive ions flow towards the electrically charged rod, whereas the negative ions get repelled and flow in the opposite direction. And therefore, there is a redistribution of charges within the electrically conducting material. This constitutes electrostatic induction in a conducting material. Normally, we assume that if there is a non-conducting material, then there will not be any flow of free ions within such a material. Ideally, our assumption is true, but practically, there will always be some movement of the electrons in the molecules of a non-conducting material also. Hence, if an electrically charged object is brought towards a non-conducting object, there are bound to be some electrons or some ions which move to one side of the molecule which face the charge. Say again, we take the same example as shown in the figure. Assume that the white object is a non-conducting material and the red object is an electrically charged object. Although the free ions in a non-conducting material will be very less compared to a conducting material. However, there will be some small redistribution of charges even in the non-conducting material. Say the conducting object has an excess of negative electrons on its surface, negative ions on its surface. Then the positive ions in the non-conducting slab will move a little towards the electrically charged rod, whereas the ions, the negative ions or the electrons in the non-conducting slab will move away from the electrically charged rod. Hence, even though we assume that a non-conducting material does not have any free flow of ions, there is still seen some redistribution of the charges within the slab itself when it is approached by an electrically charged rod. Hence, the phenomenon of electrostatic induction is present in both the conducting as well as non-conducting materials. However, the intensity of manifestation may vary in degree. This was regarding electrostatic induction. Next, we move towards Gauss's law. Gauss was a famous scientist, and his equations are one of the four famous Maxwell's equations. Again, to state in plain, simple terms, the meaning of Gauss's law is the total of the electric flux which flows out of a closed surface is equal to the charge enclosed within the closed surface divided by the permittivity of the medium. Say we have a point charge of q coulombs within a sphere having a radius r. Say the permittivity of the medium is given by permittivity epsilon. Therefore, the Gauss's law states that the total electric flux denoted by psi, which flows out of the closed surface, is given by the magnitude of the point charge, which is q coulombs as I mentioned earlier, divided by the permittivity of the medium. Here, the electric lines of flux which flow out of the surface are assumed to be exactly perpendicular at the surface. Another interpretation of Gauss's law states that the area integral of the electric field over any closed surface is equal to the net charge enclosed in the surface divided by the permittivity of space. Here, the mathematical formula for the statement is as shown on the screen. The area integral of the electric field is denoted by the symbol capital E, over any closed surface. We assume that the total surface area of the closed object is given by A. As we are considering a very small portion of the surface area, hence we have taken the area equal to dA as shown in the figure here. We take a small area dA and integrate the electric flux emanating from that area. The limits of the integral will be the area enclosed. It is given by the charge enclosed in that surface divided by permittivity of space. As such, both the interpretations of Gauss's law are very straightforward and simple. However, the importance of these two statements come to picture when we have to calculate electric fields over varying or different shapes of areas, and when they originate from different charge distributions. Both the equations that we have just discussed contribute very heavily in finding out the electric field intensity, or also in evaluating the electric field strength when you have an uneven area or an uneven charge distribution. At any point of time, we must assume that the electric lines of flux which flow out of the closed surface are perpendicular at the surface. As I mentioned earlier, Gauss's law is very important as it is one of the 4 Maxwell's equations which you might come across very soon. Please take a look once again at Gauss's law. The first statement, which is mathematically represented by psi, that is flux, is equal to Q, that is the amount of the charge enclosed, divided by the permittivity. And the second statement says the area integral, the integral is shown by the contour symbol to state that we are integrating over a closed surface. The area integral of the electric field strength over any closed surface is equal to the net charge enclosed within the surface divided by the permittivity of space. Please allow me to emphasize again, the application of Gauss's law is for calculation of electric field strengths when they originate from varying shapes of surfaces and also when the charge distribution is uneven as shown in the figure. However, at all points we must consider the electric lines of flux perpendicular at the surface. The next point we discuss pertains to the dielectric strength. Dielectric strength is basically a property of non-conducting materials, or in other words, insulators. Many a times you may come across the word dielectric in place of insulator or non-conducting materials. In simple words, the maximum voltage that can be applied to a given material without causing it to break down is known as the dielectric strength. The units of dielectric strength are kilovolts per meter, or very often kilovolts per millimeter. From the unit, we can understand what high amounts of voltages the dielectric can withstand before it breaks down. The value or the magnitude of the dielectric strength gives us a measure of the ability of the material to act as an insulator. Higher the dielectric strength of the material, better is its quality as an insulator. The dielectric material is made from a number of insulating materials or a combination of insulating materials. The most common examples being air, paper, ceramic, glass, oil, and a variety of other materials. As we mentioned earlier, the dielectric strength indicates the ability of the material to function as an insulator, or in other words, to block any current or charge from flowing through it. Generally, the dielectric strength of a material is very heavily affected by the application of high voltages. It is also affected adversely due to increase in temperature. Due to application of high voltage or due to increase in temperature, sometimes the dielectric material may break down. Breakdown basically means that instead of blocking any flow of charge or current through it, after breakdown, the dielectric material will allow any charge or current which comes in its way to flow through it. In other words, it loses its current or charge blocking capability. From this discussion, you can understand that the resistance of a dielectric must be as high as possible. Higher the resistance of the dielectric, better is its insulating property. As the resistance falls, the dielectric material loses its insulating properties, and hence, in circuits where it is installed, it becomes extremely dangerous. You might have seen many a times in our television sets or in other electrical appliances or electronic appliances, sometimes there may be a flow of current or a charge in unwanted paths. Basically, this is an effect of the breakdown or the weakening of the dielectric material used within the circuit. So friends, I hope we have been able to clarify the concepts of electrostatic induction, Gaussians law, and the dielectric strength of a material. We will quickly summarize whatever we have discussed in this session. We began with electrostatic induction, which means inducing electric charge in a conducting material or in some cases even in a non-conducting material by bringing an electrically charged object near it. It happens due to realignment or redistribution of the free ions within the material or the object under consideration. Another point worth noting is, as soon as we remove the electrically charged object from the vicinity, the free ions again intermingle and restore the neutral property of the object as it was before. Next, we discussed the Gaussians law, which helps us in the calculation of the electric field intensity over any closed surface within which charge is enclosed. And finally, we discussed the dielectric strength of a material, which basically indicates the strength of the insulation it can provide in any application. The factors which affect its performance are high voltage and variation in temperature. Thank you. I hope we have discussed, along with all the basic definitions of electrostatics, a few more concepts which will help us in understanding the behavior of stationary charges in a better manner. Thank you very much.